lesson 2 here. All right, we're going to look a little bit at historical examples of how we basically came up with some chemical substances to meet basic needs. Outline the role of evidence that and development of the atomic model, which you've probably done before, yes. But we're going to talk a little bit about protons, neutrons, and electrons. And these are some of the dudes, as I like to call them, that came up with that stuff. And kind of a little bit of their experiments. Now, don't get too worried about like what exactly did this guy. I'm going to kind of lay it out for you exactly which guys are kind of more important than other ones, and which one kind of, you know, as long as you know, like, hey, this guy was in charge of the neutron, or this guy did the proton, that's probably the most important thing. Actually, but all right. So first of all, I think we have some notes here. Matter is anything that has mass and takes up space. Some examples here are solids, liquids, and gases. Right, that's your fault. Okay, so developing ideas about matter. Ancestors of First Nations people used their knowledge about the nature of matter and processes to help them meet their basic needs. They had knowledge about the use of plants, fire, and the states of matter. So again, they had the use of plants, fire, states of matter. Those are the 3 things you want to write in the notes there. How do they use that knowledge? Well, it's kind of below here, but you know, for example, curing foods, right? Smoking food, preserving them, putting salt on foods to basically dehydrate them, things like that. Plants, fire, obviously for cooking and things like that. Making tools, for example. Use of plants would be for maybe medical purposes, things of that nature. Right, so we're going to take a little look at that. But cooking food was an important step in human survival, and so was the development of food preservation techniques, such as heating and freezing. Right, so a little bit of states there, probably. Salting, okay, basically another form of curing the meat. Right, smoking food, and fermentation. So making things like beer and wine. Developing ideas about matter. So metallurgy. Metallurgy is an early branch of chemistry that dealt with producing and using metals. And this would have been important for them so they could make tools, perhaps. Maybe in some cases like pots that they need for cooking. Weapons in some cases, I guess, as well. There's lots of anything that they use metals for, of course, would have been the study of a branch of chemistry that would have been helpful to them to do that, right? So here we go. We're going to get into a little bit of some of these people who had theories about atoms and what matter looked like and all that. And of course, you've probably heard of this guy before. His name's Aristotle. And Aristotle was about 400 before the Common Era. Matter is made up of 4 elements, he believed: earth, air, fire, and water. All right. You're going to need to write that in there. So he believed that matter was made up of 4 elements, including earth, air, fire, and water. And Aristotle was super famous at the time. Whatever he said, people were like, well, this guy, he's a famous philosopher. He knows what he's talking about. So he had a lot of influence over people, and people believed him for 2,000 years. And if you said something other than what Aristotle said, well, you know, it was hard for other people to take that seriously because he was so famous and he knew stuff. He was a smart guy. So people believed him, okay? So he believed all of the 4 elements were made up of earth, air, fire, and water. And then Democritus came along. Matter is made up of tiny particles that could not be broken down further. These particles were called atomos, okay, which is basically means singular, okay, back in the language that he had. Different elements were composed of different kinds of atoms, and he wasn't accepted at this time. He's obviously a little bit more accurate in his description at this time, but again, people wouldn't believe him because, first of all, he'd have to prove it. And even, we're going to see, even if you can prove it, people still believed Aristotle because he was so famous at the time. All right. I think we have everything there that we need. Yes. Right. Robert Boyle. So he was in 1615. Robert Boyle discovered that. He did not believe in the four-element model. He discovered the gases are made up of tiny particles that group together to make substances. Around this time, many molecules of the atoms were proposed, and we're going to look at four main people here. Okay, but this is 1650 now, so again, this is still, you know, quite early, but people were still, you know, again, people weren't believing that there was anything else other than earth, air, fire, and water. Okay. All right, so we're going to fill this in together here, of course, as we go through. I will kind of tell you, if you put something in the wrong spot, it's not a big deal. As long, when I say that, I mean like if you put the experiment or the diagram in the wrong spot or something, or you put it all under the experiment, it's not a big deal. Okay. I'll kind of go back after we're done. We'll kind of go back through and say, okay, well, this is probably the one that you should probably know, or this one, or whatever, as long as you have it down somewhere. Okay. So we're going to start with John Dalton here. John Dalton, he was about 1808, so 1808, and that, yeah, no, that's about the time he was. All right, yeah. So he based his model on the atom on experiments he did where he combined elements to form new compounds. So he basically would combine two elements, okay, and then get something new. So I'm just going to skip ahead just so you can kind of see the slides, and you can kind of decide where you're going to put what, if that makes sense, okay? Because there's two blanks here. So that is still John Dalton. So we, actually, there's this here, and then we go to J.J. Thomson. So what I would say is probably in the year part, put 1808. In the experiment, I would say you could and actually, let's go to the diagram first. I would probably write this down for the diagram and just kind of briefly say, okay, he took two elements, combined them together, and made something new. Okay, so I'd probably put that in the far column here in the diagram part. That'd probably be your diagram for John Dalton here. Okay, and then we'll go back and we'll write some stuff down for the experiment part. Okay, just some notes. But let's just use this as the diagram here, so the far right. And like I said, as long as you have this in John Dalton somewhere in that row, you're gonna be, it'll be fine. Okay, don't worry about it too much. Okay, so how do you think, obviously atoms are really tiny, so how do you think he saw reactions taking place if he combined some elements together? How do you see reactions? What are some things that you'd look for? Change in weight, sure. What else? Fluctuation of heat, so giving off energy, taking in energy, maybe. Yeah, indicate chemical changes too. So maybe a new odor is produced or something like that. We'll take that eventually here again. Color change, new precipitates are formed, things like that, right? So he would see like, he'd start with some, you know, elements and combine them together, and all of a sudden something new, like something totally different pops up, and he's like, oh, something's going on here, right? So that's what he was doing there, okay? So I think we have all this stuff here actually, so I think we're okay here. And again, if you don't have all this in the right spot, as long as you had, you know, the kind of thing there. But he basically took elements and combined them together, if you want to write down the, you know, experiment kind of thing, and saw some things being formed. We have this already. This is under the atomic model, but all matter is made up of atoms which are small, which are too small to see. Each element has its own kind of atom with its own particular mass. Compounds are created when atoms of different elements link to form molecules. And atoms cannot be created, destroyed, or subdivided in chemical changes. Okay. Now you can do that nuclear style. Okay, which is that book that I'm reading. It's all about the first couple chapters are all about the nuclear. You know, kind of back in the 40s and things like that. But that's not chemical. Those are nuclear changes. Okay, we're going to focus on probably chemical changes. Even in grade 11, grade 12, probably we're going to focus on, you know, chemical changes. We're not going to probably worry too much about nuclear chemistry because, you know, yeah, probably it's a little bit more than that. All right. So next, J.J. Thomson here. So he's 1890s here. He discovered the electron. I'll just show you kind of. This is kind of the drawing we're going to use here. Okay. And then, yeah, so that's the drawing there. I would also say we're going to use this here. My record, yeah, I'm still recording. We're going to use this, or it's called the raisin bun model or the plum pudding thing. You've probably heard of that term before, maybe, because we always use it all the time. But I would say we could probably draw a little something like that too in the diagram. But in the other part, the experiment here, in the 1890s, he discovered the electron. Okay. His experiments show that atoms contain small negative charged particles. He developed the raisin bun or plum pudding model. Okay. So under the atomic model, I guess right here, no, I can't write atomic model, okay, I would say you probably want to have that part there in the atomic model under that heading there, okay. Again, if you put it in the wrong spot, it ain't a big deal. So as I said, you've probably heard of this term before, the raisin bun or plum pudding model. Atoms contain small negatively charged particles called electrons, which would be kind of the raisins down there you see. The rest of the atom is a sphere of positive charge, so the rest of the atom was all positive. That's what he believed, the bun, and overall the atom has a neutral charge. So the atoms were neutral because they had positives and negatives all together kind of thing in this whole, okay? If you wanted to kind of have another picture here, he would say, basically say all the positives are in here and all the negatives are in here as well. And that's kind of what you had. It kind of looked a little something like that there. Right, so that's what J.J. Thomson believed. He basically, we do need to know this probably, that J.J. Thomson is the discoverer of the electron. Okay, so that's important. He's responsible for electrons, right? We do need to know that. This is kind of what he used. It's called a cathode ray tube. We actually used to have these in old TVs. This is how we used to watch. First TVs had what they call CRTs, which was cathode ray tubes. And if the tube went, you just went down to the TV store and you bought a new tube and you'd put it in. Now, you do what? What do you do with the TV nowadays, unfortunately? Throw it out, recycle it probably in a lot of cases, right? Because yeah, we have an old plasma downstairs that's still running somehow. I don't know. It's you know, but you know, and once it's done, it's done. You know, I'm not gonna. It's gonna cost you, you know, $14,000 to fix it. You know, and it's not worth that. So, but back in the day, you used to just take out the tube and put a new tube in. And I remember the tube going in the TV and stuff like that, and it was crazy. But basically, what it was, you know, it shoots kind of through here. This had a negative charge and a positive charge, and he would notice that these atoms would kind of bend towards the positive metal plate, which was positively charged, and so he kind of knew that something was going on here, and there was a negative part. But that's kind of what the experiment he used. You know, those guys were pretty smart back in the day. That, like, when I was even reading that book, the things that they would come up with are just like, wow, you know, some pretty smart guys. A little bit smarter than me, a little bit. Well, okay, a lot. All right. So if you want to kind of draw something, like, it doesn't have to be perfect. I'm just kidding. All right. Rutherford was 1909. So his experiment that he had, you can put this under experiment, I guess. He aimed a positively charged alpha particle at a sheet of gold foil. So he had aimed a positively charged alpha particle at a sheet of gold foil. Instead of it passing straight through, some actually bounced back. And we know that positively charged particles repel one another. And Thomson's theory had a positively charged cloud surrounding the electrons. This cloud would not have been strong enough to repel the alpha particle. I don't know if I can draw a good diagram of that, but basically I'll kind of explain that. But because of that, he knew that there had to be something else there, and that is how he came up with basically the nucleus of the atom. Okay. So he'll be responsible for the nucleus, but in the nucleus, he knows that that's where the protons are going to be. Basically, his theory was this. So he shoots these particles at them, and he sees that they start to, some bounce back. And I'll show you the diagram here. He uses a sheet of gold foil, basically. And he noticed that some bounce back. So at first he was like, well, the positives that are, like, if you think about back to the previous example here, there's basically a cloud of positives, right? So he just says, well, there's some this was the diagram before that we had, and then he said, well, if there's kind of a cloud of positives, that's not enough to repel. If I'm shooting these particles and they're just going, if they're getting repelled, a cloud of protons or a cloud of positives is not going to be enough to repel them backwards. So then he's like, there has to be something that's actually, it's hitting something solid and bouncing back. And that's where he came up with the nucleus. So we know now, of course, that there's a nucleus to the atom, right? And that's where you find the protons. So that's the hard kind of solid part in the middle that these alpha particles are hitting and then bouncing back. So that's how he kind of came up with that, that there's a nucleus here, and that's where you're going to find these protons, right? So the diagram kind of looks a little something like this, okay? So he aimed at these alpha particles here. Some kind of pass through because, of course, maybe it goes right between some of the atoms kind of thing. So in some cases you get lucky. Some maybe bend a little bit, so they kind of get deflected a little bit. Maybe they kind of hit the side of the nucleus or like the bottom part. But some, okay, and you can actually, this is probably the best diagram here. This is kind of what he expected to see, okay, is that they would maybe get bent a little bit in one way or another. But this is really what happens. Some pass through, some maybe get deflected a little bit, but some actually hit the nucleus by chance, like this one here, hits the nucleus and then bounce back. Okay, and that's how he came up with the fact, okay, well, there's got to be something in the middle that's causing that to happen. That's the nucleus. And in the nucleus, that's where we're going to find the protons, of course. Okay, so that was his thing. You probably should know this example. So the gold foil example is his example, and you should know that. Okay, that's probably going to be on a quiz or a test someday. That's kind of his result. It's kind of a big one for us, so we want to know that. Okay. Okay, Rutherford model is next here. We did that one, but again, an atom has a tiny dense positive core called the nucleus that contains the protons. I guess if you would like to write that down, that might not be a bad idea. The heavy nucleus is surrounded by empty space that contains rapidly moving electrons, and that's why most of the alpha particles pass straight through. So maybe we want to write that down somewhere, I guess. Wherever you have room that fits is fine. Okay. I guess you have that, don't you? Well, you kind of have that, don't you? Yeah. I guess it's already under the atomic model there, right? Yeah. So I guess you have most of that. You probably don't need to write that down. It's probably there. Good. Okay. My bad. I should look a little closer, I guess, eh? All right. Neils Bohr, 1885 to 1962. Now, I don't expect you to draw that, of course, but 1885 to 1962. Experiment, when elements are heated, so this is experiment, you can put that in there for sure. Oh, that's already there actually, eh? Perfect. When elements are heated in a flame, they show a few specific colors that can be observed with a spectroscope. These colors are called the line spectrum. So as you heat up certain elements, they give off certain colors in some cases, all right? Sometimes I go to lab and I can kind of show you that in fact does happen, okay? We don't usually use elements, but I mean, it's kind of the same idea. All right. All right. So the Bohr model, okay, this is what you're going to have to write down in the model here, explains the light spectrum observed. When electrons are energized by heat, electricity, or light, they can jump from a lower energy level, which is known as a ground state, to a higher energy level. Right? And when when they jump up, they take on that energy, electrons do. When they fall back down, okay, they emit a light in some cases. Okay, they give off light. They use that to kind of see how much light was given off, colors, things like that, and they can observe that. So I'm sure I probably shouldn't be talking right now because you guys are writing notes, so I'll let you guys write notes here, and then I'll. An example of this, by the way, would be neon lights. You know, when you walk into the store and it says open, you know, those are plugged into the wall. So neon lights, of course, use some neon gas, but when they get excited, they jump up to the next energy level. When they come back down, they emit a certain color. Okay, and I'm sure you've heard about the Bohr. Have you heard about? I'm sure you have the Bohr model before. Yes, Bohr, Rutherford. Sometimes they kind of combine them together. Once we get to Chem 20, we kind of drop that a little bit, but basically that kind of looks like a circle, right? There's a nucleus, and then these electrons go around the outside in specific energy levels, and then they kind of jump up, and when they come back down, basically this means that this electron falls back down and emits some light, okay? A different color light will be given off depending on what energy level the electron starts from and jumps to, and then falls back down to, okay? So I guess you could use that as a quick little diagram there. Quickly here, so 1885 to 1960 proposed that electrons surround the positively charged nucleus at specific energy levels. Okay, I guess I would put that underneath the atomic model, probably somewhere there. He basically said each electrons have specific energies, okay, and they're found on these different levels. Okay, the first energy level, second energy level, third energy level, yes, okay, and so on and so on. And I'm probably going to ask you at some point how many electrons go in the first energy level, and you're going to tell me what? Somebody, not these guys over here. Somebody back there. No, not you. Anyone? How many electrons go in the first energy level? Remember? No? Maybe we don't know this. I don't know. Maybe I'm just assuming. Yeah. 2. Yes. How many go in the second one? Does this sound familiar now? How many go in the second one? No, not you. Anyone over here? Yeah, 8. Yeah, and so we'll talk about that again. If you're like, I don't know what you're talking about right now, it's okay. We're gonna do that. Okay, it'll be fine. No worries. But yeah, it goes 2, 8, 8, and then after that it gets a little complicated. Okay, but we'll talk about all that. Yep. And if we don't finish, that's okay. But I'm gonna finish this actually. But I'm still gonna make you guys do the homework here because you can probably do most of it, I think, for the most part. So we are gonna do the homework at the end here. There's 6 questions. Do your best, and we'll talk about it tomorrow, kind of thing. But I want you to do some tonight here. So evidence of the neutron. Okay, Rutherford and his colleague Chadwick proposed that there was a third subatomic particle. It's called the neutron. He noticed that helium contained, okay, twice as many protons and electrons as hydrogen. However, helium is 4 times heavier than hydrogen. And so this had to be due to the presence of a third particle called the neutron. Okay. I'm going to finish this off here. I know the bell's going to go soon here, but that's okay. All right, good. And lastly here, I need to record the rest of this, I think. Today's model is based on the theory of called quantum mechanics, okay? Electrons are thought of as a cloud of negative charge that occupies the whole space all at once at different energy levels. I'll go over this a little bit more tomorrow as well, so don't worry. But the electrons surround the nucleus that contains protons are positively charged and the neutrons are neutral. So in the nucleus, we have the protons and neutrons. And then, of course, we have a cloud of electrons that surrounds that, okay? That's what we believe today. We do not believe that we can particularly find a specific electron somewhere, all right?